All right, welcome back, everybody. I hope everybody got a good break, and you're now back for session 4 of GAPS on instabilities. So, just as a quick reminder, each speaker will have 15 minutes, and I'll be giving a 2-minute warning. If you have questions for speakers or comments on the topic in general, everybody, please go ahead and post these in the Slack under the session 4 instabilities channel. And then we'll use that as the basis for our discussion. So I'll be noting and drawing everyone's attention to some of those key comments and answered questions. And I'll encourage folks who participated to raise their hands and then chime in here to add to the Slack discussion, to add to the Zoom discussion. So we'll start off with Jared Goldberg in this session, and he'll be speaking to us about 3D radiation hydrodynamical simulations of red supergiant envelopes and 1D insights. So go ahead, Jared.
Cool. So hopefully you all can see my screen.
Yep, it looks
If
great.
not, chime in. Great. So thanks for having me, and I'm excited to be here. It's a little early, but hopefully the caffeine's kicked in by now. I'm on the West Coast in California. I'm a PhD student at UC Santa Barbara, working with Lars Bildston, Yang Zhang at Flatiron Institute, and a bunch of other people, in collaboration. And I am interested generally in massive star envelopes, red supergiant envelopes in particular, and I got into this kind of from the core collapse supernova light curve understanding end. So when stars explode, they can tell us a lot about the structure of the star, and similarly, the structure of the star influences what we see in observations. And so I talk a lot more about that in my 5-minute talk, and I encourage you to check it out just as a little bit more about the structure, but here I'm going to be talking about some 3D simulations of red supergiant envelopes. So before I do that, though, I want to mention red giants because this is a conference about both. And red giant convection has also been realized in 3D, and there's a lot of interplay between red giants and red supergiants and connections and similarities and differences to be aware of. There's a lot of prior work on atmospheres, t-tau relations in red giants, calibrating alpha, the mixing length parameter to the surface, surface convection, and the atmosphere with references here. Also, simulations of red giant branch in AGB star convection in the interior reveal large-scale coherent fluid motions that we're also going to see and understand a little bit better in 3D red supergiant simulations as well. And here are just some density slices from Bren Freytag's and others' work in 2017. And here's, we also see these, just a handful of plumes across the surface of the star in red giants. Now, the red supergiant regime is similar, but there are a few notable differences. First of all, the luminosity scale is a couple orders of magnitude brighter. So in the interior, radiation pressure impacts the gas dynamics. Here on the right, plotting versus temperature so that we can get red giants and red supergiants on the same figure. I'm plotting P rad over P gas, the ratio of the radiation pressure to the gas pressure for red supergiants in the non-red lines, and then the red giants star Maiden Mesa down here. And we notice that the red supergiant radiation pressure is significant throughout the envelope, and the red giant radiation pressure is not. Also, the convective velocities in red supergiants become nearly sonic and go significant, very deep within the envelope, even before hydrogen recombines at 10 to the 4 Kelvin. Whereas in red giant branch stars, the convective velocities only reach half the sound speed, even in the coolest parts of the star. Additionally, in red giants, radiation transport becomes significant for energy transport below tau of about 100, where the local the luminosity is only about 0.1 Eddington at that location. Whereas in red supergiants, this happens at tau of 400, a little bit higher optical depths, and the luminosity near the near the radius where radiation transport starts to become relevant for energy transport is actually locally super Eddington at about double the Eddington luminosity. And even at the tau of 100 location, the luminosity is still near Eddington. So these stars are close to blowing themselves apart. So more insights from 1D modeling. Well, our favorite instability, convection, matters a lot. And actually, the assumed efficiency of the convection, the mixing length assumptions, really have a strong effect on the temperature, on the effective temperature, and thereby the stellar radius. So these are now just 4 red supergiant models made with, they're all 16 solar mass. They have roughly the same core, same luminosity, solar metallicity models in MESA, and varying alpha, we see that the radius of the star can be anywhere from a few hundred solar radii out to over 1,000. And all I'm really varying here is the efficiency of convection in the envelope. And more than that, the pressure scale height for all of these is a significant fraction of the stellar radius. So if alpha is a few times the stellar radius, if alpha is 3 and the scale height is 0.3, then we assume that the size of the convective cells, the lighter bubbles moving outward, is going to be roughly of order the radius. So there may only be, and it's not surprising that there's only a few plumes. And we see this also in red giants, models of red giants as well. And then again, this significant radiation to gas pressure ratio implies that the envelope is not a simple polytrope, but rather that the radiation pressure and gas pressure both matter, and the relative ratio, as it changes, also changes the equation of state. So there's also existing work on red supergiants that focuses primarily on understanding the outer convection in the lossy region, or in the region where radiation transport starts to dominate the energetics, or the dominate the flux. And there are references here. And we also see a handful of blobs distributed across the surface of the star. I think a lot of us saw movies like this recently in press when Betelgeuse had its great dimming event and everyone was talking about pulsations. And this is what the simulations say. But we wanted to go deeper into the star to try and calibrate the mixing length, and also to try and better understand the surface, better understand connections between the bulk motion in the interior and then to the surface. So we turned to an Athena Plus simulation, which we ran. The inner boundary we put at 400 solar radii, which is inside the convective region, but we match profiles from a 16 solar mass MESA model, using a spherical polar grid with resolution shown here. Our equation of state is ideal gas and radiation, and gravity is included as g times the enclosed mass over the radius. Because these envelopes are loosely bound, having gravity right, we think, is pretty important. We then solve radiation transport with opal opacities for the full radiation hydro solution. So it's not the diffusive approximation. We use Yanfei's rad hydro module in Athena and see this paper for implementation details. And then we supply luminosity at the bottom boundary by a hot plate. We increase the temperature at the inner boundary, or by a heat pump with a fixed region of constant L. And we've run a few of these models, and I'm going to mostly focus on discussing one here for clarity. So what do we see? We run this for a long time, about 12 to 13 years, until we reach what we think is a steady state, or an equilibrium. And in the interior, we recover a flat or roughly flat entropy profile, which entails that the convection is more or less efficient, or nearly adiabatic. And then the decline here starts to indicate superadiabaticity in the very optically thick limit, and then indicates radiation transport starting to matter in terms of carrying the flux out past 700 solar radii for some of the fluid. And this dashed line here shows roughly the location where convection dominates the energy transport versus where radiation dominates the energy transport. And there's this high entropy outer region, and this is actually what we see, or what we'd observe. But getting both, understanding both, I think, is very important. We also see the same kinds of large-scale convective plumes as seen in the cobalt simulations. So here is a time lapse at 650 solar radii. The color is just radial velocities. So red stuff is moving inward, blue stuff is moving outward relative to the bulk flow. And it's colored because in classical convection, hot stuff rises and cold stuff falls. and blue is hot. We can also turn to a radial lapse, so we pick a fixed point in time and then move outward in the star, and we see that the structure, the convective structure, is pretty coherent. We want to stay a little bit away from the inner boundary to make sure that no effects of the inner boundary condition are really mattering, but uh, the general structure out from 500 solar radii near the surface is still pretty similar. We see the same kind of large scale coherence. A little bit more about the turbulent structure. Radiation can carry a significant amount of the flux at tau of less than this critical tau, P rad over P gas, C over V. It's normally in radiation dominated regime, C over V is this key variable where light can get ahead of the convective motion, but because we have to evacuate the radiation field, P gas over P rad times, or P rad over P gas time, no, P gas over P rad times, the critical optical depth is modified by that. Convection therefore dominates at tau greater than tau crit, radiation transport dominates at tau less than tau crit, and we can see that here in the lower panel are plots of the optical depths along different lines of sight, and this black line is the value for the critical tau, P rad over P gas over V. Out in this 700 to 800 solar radius region is when radiation transport starts to matter for the energetics and for the flux. And that's reflected in the luminosity profile. Here I'm showing the radiative luminosity in our model, with the scatter being the scatter in the model. The color is log probability that you'll find a fluid element at a given location. Getting a given radiative luminosity. And the difference between the flat line and this is going to be what the convective luminosity is making up. And then additionally, turbulent pressure is large. It actually exceeds the thermal pressure near the outer parts of the envelope. And so this also needs to be taken into account when modeling convection in red supergiants in 1D and in general. Now, outside this critical tau of location, the fluid motions no longer resemble classical convection, but there are still turbulent fluid motions. In fact, the denser material starts to move outward. And here I'm just showing on the bottom panel is the correlation between the radial velocity and the density. So when it's negative, the denser stuff is falling. And when it's positive, then the denser stuff is rising. And we think this has to do with the fact that these models are near Eddington luminosity in the location, near and above this tau crit. And this is the area fraction where tau is greater than tau crit. So inside 700 solar radii, everything is very optically thick, and radiation transport really doesn't lead to a whole lot of energy transport. But then outside, this radiative diffusion is dominating the energy transport. We can also check the convective velocities against mixing length theory. And inside the classically convective region, the velocities agree pretty well with rough predictions from MLT. The black line here is the RMS velocity, or 1/3, the square root 1/3 the RMS velocity, which would be the convective velocity. And the gray areas indicate 68% of the fluid being between velocities of 3 to 9, and 95% being between 2 to 10. And the colored lines are what MLT would predict, given by the equation in the upper right-hand corner. One of the things that we see here, and actually in red giants, is that these coherent plumes lead to a flatter velocity profile, that it's really not a local problem. And we see this also in red giants. This is from Palacios and Brun 2009, with
2 minutes,
velocities.
Jared.
Great. Oh, okay. With these velocities here. Okay, so we then, because we want to calibrate the mixing length, there are calibrations to observations, but so far no 3D red supergiant regime calibration of the mixing length physically motivated, we can compare the 1D time average profiles to mixing length, assuming different alphas, including turbulent pressure. We find that alpha is 2 to 3, which is actually in rough agreement with observations of red supergiants on the HR diagram compared to 1D models, particularly this Chun et al. Paper in 2018, but then also some of the references that I listed on an earlier slide. Um, and the thing to stare at here is the overlap between the black line and the orange and light red solid lines, this gradient grad, which is d log p d log t, an important term in understanding the convective instability, and that it tracks really nicely with alpha of 3 and then starts to go down to alpha of 2 out in this outer region. So some takeaways, we have this nearly flat entropy profile with, in the interior with a hot outer region. There are large-scale coherent plumes throughout the stellar envelope. We have calibrated alpha in a physically motivated way rather than to observations, both of which are very good and important, I think, to be 2 to 3, which is, and we see nice agreement there. And there's more to come, so keep watching this space. Further questions, food for thought. Do different, how well do different methods of calibrating alpha MLT, both observationally, theoretically, and the different ways you can calibrate it theoretically to 3D models, how well do they agree? What are the best ways to incorporate this important turbulent pressure contribution into 1D models? Currently, the state of the art is pretty rudimentary, if not non-existent, for incorporating turbulent pressure into 1D models. How does surface convection and the surface convective motion couple with things like pulsations, like we saw in Betelgeuse, winds, all of the topics of all of the different things. And then I didn't even touch convective boundaries or overshooting in this talk, but there's a lot of work done there and a lot of interesting things to think about there. And the interplay between all of it is important. And so thank you for your time. Thanks for having me. And I yield for questions.